High-speed craft, naval vessels. Oops. This one I showed the last time, and I thought a little bit about it, that I should say maybe a little bit more about hydrofoils. Hydrofoils was a very hot topic if you go back to 1970 approximately, even before. There was great hopes about hydrofoils as an efficient way of going high speed at sea. And you know the principle, well, probably a little bit, but we'll go more into it. So the whole point is to lift the craft out of the water, and the way we do it is by using foils. So what you see here, oops, where did I put my pointer? There, too many pockets. So you can see here a rather big one that is foil cat lifted out of the water, and under the water you'll find a number of foils. Here you see 3, but in many cases it can be much more. It all depends on how much lift you need in order to carry the weight of the craft itself, as well as, of course, the passengers. And so you can see different configurations. You can see here at the front you can have a big foil and a smaller one there. You can have a small here and a big one there, or equal size, or you can split them and thereby get maybe better stability, like you see here. And in some cases you see 3 rows of foils, and it's all because we want to get more lift. And as you know from when we were talking about wind turbines, we were talking about lift as a function of the curved shape, where the flow has to go a farther way and have higher velocities on the upper side than on the lower side, and higher velocity means lower pressure, so you have a force resultant as a function of this curved shape. But also remember, we talked about the angle of attack. So even a flat plate, a flat plate that is not curved, if we push it through a fluid or through water, it will tend to move upwards in relation to, if we push it like this, it likes to go up like that. That's because of the angle of attack. So, of course, when you are traveling high speed on sea and you have waves and you have different conditions, you will have to have some kind of dynamic control. So typically some of these foils you will be able to move up and down, and through a system, oops, nobody heard me over there. Okay. Through a system that will respond to the motions. So, of course, with this high-speed craft, you would like to go as smooth as possible, but the water is moving by itself, and of course that will also affect the foils that are in the water. So, therefore, you would like to shift the angle of attack, typically, to control this motion and make the ride as smooth as possible. And there are, in principle, as you see here, the foils that are fully submerged, I think in the 70s you saw a lot of catamarans looking more like this, with foils that went like that. So let's say you had something like that. And the idea was possibly to not have more foils in the water than you needed. But in reality, the stability of such a system is less than certainly the dynamically controlled submerged system. You can imagine if you have waves coming up here, right, on one side, and maybe going down on the other side, you'll have a tremendous twisting moment on this craft. So I think most of the hydrofoils you see today are fully submerged. So in some cases you will see these hydrofoils. I'm not sure how common they are in Korea. Have you seen any here? No? They are not particularly seaworthy. Here, for instance, you see a hydrofoil operating on a river in China, on the Yellow River, right? So it's rather smooth, and the advantage is that you don't have to go very deep. So if the river is rather shallow, it can still operate. What we also saw in the 70s, that was typically the Lockheed Martin and Boeing saw this as a new opportunity to go into shipping, right? Because in one way, with the wings and all that, it was quite similar to aircraft. And weight is important, so light, strong structures like you find typical in aircraft. This one doesn't look very stable, does it? Certainly, the control system has to function 100% in order to be able to operate a situation like that. But, there are aircraft that are aerodynamically unstable. Some of the fighter airplanes are not stable in air. It's completely dependent on dynamic control of the flaps. So it's possible. And of course you have to have sufficient power to lift up the entire craft out of the water as well. So, and when you look at some of these, obviously to make them bigger, well, what has happened? They have several sets of these foils in order to increase the lift capability. And that means also you get more drag, and of course you need more power. But as far as I understand, in addition to the drag problem, there's another problem with hydrofoils, and that is cavitation. So if you list this, relatively high speed, but 35 knots, well, it's like a big naval ship can do 35 knots displacement hull. So it's not, it kind of hits the wall when you get to 35 knots. And that's because of drag, and I think it's also because of cavitation around these foils. You have to make them large in order to get into rough seas, and the advantage small draft. But, resistance with high speeds, cavitation, and fatigue, and I'm not sure how competitive they are when it comes to fuel consumption. But my impression now is that surface effect in terms of planing. You know, when you have a light hull that can plane on the surface, it's more efficient, even though you have, of course, skin friction. So you can go higher speed. And there's another type which is also sort of competing with hydrofoils, and that is what is called the SES, surface effect ship. So, in the surface effect ship, you see we typically have a twin hull, sort of a catamaran, right? You see there? And for instance, in Norway, we have built many of these in glass fiber reinforced composite as a counter vessel for mines and things like that. Because, of course, some mines can be triggered by magnetism. So some of these minesweepers or countermeasure vessels, you know, are made non-magnetic. So, and we'll look a little bit more at this principle of the SES. You see some more of these. Russian, the Swedish. Here you can possibly see that there is something in front here, and it's actually what is referred to as a curtain, a rubber curtain with sort of fingers.
Are they using what is it?
Using
water
jets. Yeah, I think that is typically what you have with these. So here you see the curtain in front. So you can make pretty large vessels. You see this is more than 50 meters long. So you can make these larger than I think you can make a hydrofoil, right? In principle, there's no reason for not making even a bigger. But of course, the principle here is that you have an air cushion under the ship, and we'll look at how that looks. And of course, again, it is quite important to have a rather light structure. So what is happening? Well, you have these two twin hulls, and you have some big fans, not just one, you have several big fans, and in principle you blow air in here, you see, and when the air pressure is increased on the inside, you see you pressure, if you think of this as a static problem, you pressure the water down. So in this case, maybe the difference in water height between the outside and the inside is about between 0.5 meter and 1 meter. What does that mean? Well, if you have 1 meter difference between these two surfaces, it means that you have a lift force comparing to how much you have pressed down the water, right? And that, if it's 1 meter, it means that you have pressed per 1 cubic meter water per square meter, that is 1 ton force per square meter. And of course, if you have a huge space between these two hulls, you can lift many, many tons by having such an overpressure. And you know, 1 meter waterhead, 1 meter waterhead, how much is that compared to an atmosphere? 0.1 atmosphere, right? Because 1 atmosphere is about 10-meter waterhead, right? So it's not, it's not that much pressure you need to apply, but still, by having many square meters with this overpressure, then you get quite a lift from this air cushion that you have in the ship. But you can see also there are some disadvantages when it comes to the stability of the vessel. And I don't think this figure is particularly good. I would rather calculate the second area moment based on this, or you can do the whole and subtract the middle part of it. But anyway, it has some implications for stability when you have an air pillow under the ship. And I think we talked about this principle of air pillows, remember, when we had a floating city or a mega floater. We talked about having air under a floating block, and this is more or less the same principle. So here you can see the forepart of the ship, the bow, with these inflated fingers. It's a double curtain which is sealed along certain distances from each other, and then you blow air, and so it's flexible. And of course it has to be flexible because this is going to hit waves, right? This is the forepart of the ship, the bow, so it's going to hit all these waves. And but the thing is that we need to seal the air pressure under the ship. The sides are okay because there you have the holes going into the water. And the air pillow at the aft part, the stern, you see it's often made like this, 3 pillows on top of each other. And you want it to be flexible because it's kind of the rump of the ship that is sitting on the water, and it will to some extent vibrate when the waves come in. There are also waves inside this air cushion chamber. So if you look at a ship like this, let's make it just simple. And let's say you have the water level here, and then you have extra air pressure, right? And this distance here is what gives the lift, right? You can see that's just a simple way of seeing how much lift you get as compared with the how much the pressure you have, right? The pressure can be translated to water head, and then it's kind of doing it by head how much lift you get. But of course, if you think of this, you have a mass, a total mass for the ship, and of course you have what could be looked at as buoyancy springs, right? And we calculated the heave period for a submerged body, right? In that homework. So that is, it's the water plane area. Rho G is that hydrodynamic spring. So it corresponds to, I'm not quite sure how this is when you have, well, it's this point and this point. That is the important thing. And similarly here, you can look at this as an air spring, right? And you can calculate, and I'm not going to do it for you. You can do it yourself. But you can see if you move the ship down U, you move the ship down U, what is happening with the air? Well, the air is compressible. Water is not compressible, but air is compressible, right? So if you have initially a pressure P0 there, you'll see that by pushing down the ship, the pressure goes up. And how much it goes up? Well, the spring constant for this air cushion is simply the coefficient that gives the increase in the lift force, right? And you can relate that to H, but you know the gas law. So P0 V0 equal P0 plus delta P times V0 plus delta V, right? And these quantities you can express as a function of U. And by doing that, you find the spring constant for the air. So we have two spring constants, one from the displacement and one from the air cushion. And of course, when you have the spring constant and you have the mass, you can calculate the heave frequency or heave period. And this is a tricky part for these vessels. And that has to do with, you have, let's say you have something like this. And you have some cushions here, and you have some cushions here, and you have the water here, and then you have the water here. And of course, you understand this? This is because of the additional air pressure inside. And if you run into waves, right, and if you have a wave that goes like this in principle or goes like this in principle, you see you have a great effect on P, right, on the pressure. And if you are unfortunate, let's say you have a wave length which is consistent with when you travel at a given speed and you have a certain wavelength, of course that will give you a excitation period, right? So this ship travels with a velocity v, and it hits wavelengths of a given quantity, and you can see that if you are unfortunate, so you'll hit waves with the same frequency, incoming frequency, as the heave frequency or the heave period of the ship. And when you sit inside, and for certain sea conditions, the whole thing vibrates. It's so that you cannot read, or your coffee cup is jumping around. And this has been a problem for this kind of vessels. And the way they have tried to deal with it is when you have these pressure variations inside. If this is pressure P as a function of the time, right? So what they try to do is to remove air when the pressure is building up. And so they have vents that open and close, open and close, open and close to counteract, to have smaller effects on the pressure variations under the ship. We want the lift. We want the lift from the pressurized air, but we don't want these big variations in pressure, because that is going to shake the whole ship. So, interesting problem. So it's not a simple technology, and it's used for certain types of ships. I think today we see less of this SES than before. The high-speed passenger ships are normally just, let's say, regular catamarans or twin hulls. That's what we see more and more. But of course, with a shape that gives a surface lift, and thereby, get some lift effect on the vessel. But certainly these SES have one advantage, and they can go terribly fast. So there are serious productions of these passenger vessels that go 55 to 60 knots. So that's almost twice as fast as a hydrofoil, right? So the potential is there, technically complicated. And of course, if you travel in sheltered waters, it may be not such a big problem with this cobblestone effect, as it's often called. When you got the brrrr, you hit the waves, you hit the incoming waves at the frequency which corresponds to the eigenfrequency in heave, which you can get from this kind of consideration. And you can find a lot of exotic things when you look at internet, of course. So that's ONR, Office of Naval Research in the United States. They have done very many concept studies, like the floating airport project in the United States. And they were looking at landing vehicles, right, to be able to go ashore. And you see many variations. This is like air cushion thing. This is like a SES. There are combinations of ships where you have, well, at least some sort of, it looks almost like a swath, doesn't it? And then you have these landing vessels that are this caterpillar type belts. So here is also air cushion variation, etc. So we'll look more at some of these things. Of course, with modern CFD, you can do rather complicated analysis of, two-phase fluid, both the air part, which is important, and the fluids part, right? And as you can see, the military has been driving some very exotic projects. This is a swath, and what is the purpose here? It's to be stealth. Stealth means that it will give a minimum radar signal, right? I'm sure you have seen pictures of these stealth airplanes with a faceted surface, flat surfaces, and that is because the radar signals will not be reflected in a wide range of angles. It will only be reflected in one, which is different from the incoming direction of the signal. But to me, I'm not sure. Doesn't look too stable, does it? And of course, a swath that has most of the buoyancy underwater. Remember, the swath looks like a torpedo in the water. That's where the buoyancy comes from. So it's limited how much carrying capacity you can have on the swath. And of course, when it comes to stability, well, the stability probably will have to come from sort of dynamic control with some applets, some winglets on the submerged body. So probably some control system. But of course, the disadvantage or the drawback by this dynamic control, what is that? Well, you can imagine if you stop the vessel, right? You are stopping because you're going to do something, maybe let people off or something. Of course, the dynamic control systems don't work unless you move, right? So when this stops and there is, let's say, a sea condition which is exciting the dominating roll period of frequency, then you could be in severe problem because there is not much stability in roll here because there's such a small water plane area, right? And when I look at this picture too, I'm getting kind of look at these big waves. I'm not sure why it generates such a wave pattern. It doesn't look very good. So I'm surprised they got as far as building one, because that should be possible to discover in a test basin. But people have been doing very strange things. So going now from catamarans, one can look at trimarans. This has actually been built. So you have a very slender main body, okay, this hull, and of course it will be terribly bad in stability, in roll stability, and therefore they have these appended some extra hulls, so to speak, on the outside, which helps in stability. The same here for a naval vessel. So these are displacement based on hydrodynamic buoyancy, but the idea is to have a rather wide, here in this case, a rather wide deck area, and stability provided by these two extra hulls on the sides. Of course, when you do that, you increase the skin friction, right? So you can reduce the viscous friction, from the aft part of the ship, because the hulls are very slender, but you get more surface area touching the water, and therefore more skin friction. Sailboats, that is really, really high tech. It's like Formula One for cars, right? What is invested in things like America's Cup or Volvo Around the World cup. It's just amazing. So you see some very, very sophisticated designs. A catamaran sailboat can go much faster generally than a monohull sailboat. So some of the speed records that have been set are for catamaran or twin hull or even trimarans. See? And you see typically if you have two hulls, you'll end up with a situation where one hull is completely lifted out of the surface. That may happen, of course, also for a trimaran, and I guess it has to be designed for such a condition, but in most cases, it's standing more horizontally. It's not lifted out of the water. And that, of course, has the advantage that the mast is standing vertical and catching more wind than when the mast is leaning over. Okay? So these are high-tech vessels with typically carbon fiber reinforced hulls, maybe even carbon fiber in the sails, etc. And some of these ideas have been extended to more conventional, in one way, merchant ships, commercial ships. So it's not only for military vessels. And this is a concept study for a fast-going container ship, which they have made very, very slender, and thereby reduce the overall resistance of it. But of course, if it's slender, you have the problem of stability, and therefore you need these appended hulls, smaller hulls on the sides. And of course you'll get very large forces in this type of structure. And of course, one may also wonder about how smart this is, because if you make the hull very narrow, you are reducing the carrying capacity in terms of number of containers. Well, of course, if you make it longer and more narrow, you may be able to meet your requirements as to cargo capacity. So obviously there are some advantages maybe in saving fuel. There may be some disadvantages in terms of cargo capacity. Also the sea keeping, how this is behaving in the storm condition or in severe weather condition is also a question. But as we talked about, these days one is possibly more concerned with saving fuel and going at slower speeds than one is with going for the high-speed case, right? That is because of the environmental impact, and it's because of the cost of the fuel. And this is another concept. And there have been quite a few studies of this type. You see, this one has not only two additional side hulls, but it has two more in front. And you can see some of the model testing that has been done. So there have been some very serious concept studies. I don't think any full-scale ship has been built like this, and I think part of the reason is that the focus now is more on environmental performance than on speed. Yeah. I would think also, can you think of another disadvantage when you, let's say you want to go from the Atlantic to the Pacific? I think you'll probably have some problems in the Panama Canal, right? Of course, the Panama Canal now allows ships of the beam 32.2 meters or something like that, and it's going to be 48 or 49 after the widening.
It will be
48.4. Okay, so that's good. So that's the official number. I knew it was somewhere between 48 and 49. So it's 48.4. And of course, this is probably not a good design for any canal, I don't think. So it's difficult to come up with an entirely new concept that only has advantages, right? There are always some disadvantages, unfortunately. So that's why we often say that most innovations are more of an incremental nature rather than revolutionary. Because you could say a hull like this would be rather revolutionary. But certainly there are some difficulties. So one should, of course, try to be creative, but before you go too long in the process, you have to come up with the arguments against the concept. And so the concept has to be vetted, it has to be critically assessed with regard to what the disadvantages can be. And it's very strange to see things that actually have been built. Look at this. It's built by Lockheed Martin, obviously with military money. And it is a swath type. You see the main buoyancy comes from below the surface. Rather small waterplane area. But it doesn't look right. Simply. So again, I'm quite surprised they got as far as building one. But maybe they gained some experience, and sometimes, a wild idea proves not to be very smart in the end, but there may be certain aspects of a wild idea that could turn out to be, in a modified way, to be useful. Okay, let's do a little bit of hovercraft and then we'll stop here. So the hovercraft, and it's not hoovercraft, hover means to be up in the air. So you see, it doesn't have any propellers underwater. The propulsion is by air propellers. And of course it has a hull because it can sit down and float. But when it's operating, the whole thing is lifted more or less out of the water. So it's similar to a SES, but remember a SES always has two the twin hulls down in the water, right, on the sides. Whereas a hovercraft typically will have a curtain, a inflated curtain around the entire periphery of the hull. And there is one great advantage by a hovercraft. Here you see the principle, by the way. So you have sort of a structure. You have the fans that are blowing in a lot of air, but you have to blow in much more air than you do for SAS, because this is entirely based on airlift. But these are extremely noisy. I have traveled on one, and you really have to have air protection to be. It's the combination of the fans and the propellers. The whole thing is shaking, vibrations, and of course, since you are resting on an air pillow, it's rather unstable, right? Where does the stability come from? Of course, it can't lift very much. And these rubber curtains are also wearing out quite quickly. But the advantage can go on water and on land. So typically they can go up on the ramp and sit down on land, and the passengers can go on and off, and then it moves out at sea with this air pressure and can move along. So that's the hovercraft. So strategically, it can be advantageous, particularly for military purposes, but I don't think it's a concept that is very much in use for civil purposes. Okay, then we'll take a break and we'll talk about VIG and a few other things during the next hour. Questions? No? So, this is somewhere in between aeronautical problems and nautical, right? Ship type problems. Okay, let's start again. So we'll finish with the high-speed craft, and what we have been talking about is the more conventional hydrostatic buoyancy, right? Or a displacement ship, which is often referred to as powered lift, which could be like we partly have for a SES or for a hovercraft. And then we have hydrodynamic lift, which could be hydrofoils, right? Or it could be a planing surface that's skidding on the top of the water, right? You can get the lift effect that way. But then this triangle has been extended to a tetrahedron because we not only get lift from the water and the conditions under the surface, but we also get a wing effect. And then we have what is called a WIG, wing in-ground effect, which you'll get also when you're flying very, very low above ground, or you are flying very, very low above the water surface. But typically these WIG airplanes, they land on water. And have you heard about the spruce duck? There was a movie made about the life of Howard Hughes. He was a multi-billionaire within mechanical industry, and he also was spending a lot of time in Hollywood. And this is from the harbor of Los Angeles. He built aircraft, used aircraft, and he wanted to build the largest aircraft ever. And in those days, this was before the Second World War, they had great belief in planes that could land on water. So look at this, all these propellers. So he built this airplane, but he could not get it high up in the air. It only flew a few meters above the ground or the water surface. And there was a good reason for that, because the airplane didn't have enough lift to fly in a regular fashion. So if you look at the airflow around the wings, of course, you have some pressure waves being generated by the wings, because the wing is forcing its way through the air. But you can see that if you're flying very, very low above the surface, you kind of build up extra pressure under the wings. It's like a pillow. Well, it doesn't have any curtain on the sides, but it's a similar effect. And that's what really happened with this spruce duck, that he was benefiting from this effect without fully understanding it, but they couldn't make it fly like a regular airplane. So one could increase the lift effect without increasing the drag effect. And this, of course, can be interesting, and particularly in the Soviet Union, former Soviet Union, and now Russia, they have been pioneering this kind of airplanes. So they are not designed to fly high up in the air. They are designed to benefit from this interaction between the wings and the ground or the water surface below. Of course, a plane like this would be no good on land, would it? Suddenly there's a building or a telephone pole or something. Whereas on water or on ice, level ice, it could be okay. So that's what they have developed quite a few versions of. And you see, this one is a missile launcher. So this is, by flying close to the ground, you can increase the lift considerably. So if the lift is 1, you can see you may double it or even more. But it has very much to do with the wing area. So many different concepts have been not only designed but also built. And I think the Japanese also have been working in this field with small aircraft. I think this is Japanese. And in one way they are safe. You don't fly so high up, but then again you can only fly over water, right? So there is a disadvantage. And how this performs during rough sea, I'm not sure, but I think you probably would get this kind of cobblestone brr effect also if you are unfortunate when it comes to frequencies. And of course, Korea cannot be less sophisticated. So this, I don't think it's been built, but 20-seat big ship or airplane, 77 meters long, 300 tons, 250 to 300 kilometers an hour, similar to KTX, all right? So you could have a KTX going along the coast without having to build a new rail. So where that project is at the moment, I don't know. Of course, one has limitations as to what kind of sea conditions one can land in with a plane like this. And things are getting even more crazy. You see this one? It has air wings, but it has also kind of a hydrofoil. You know, again, you have to start thinking. What kind of speed do you have to have in order to have significant lift in air? Well, I think you would have to have, let's say, a couple 100 kilometers an hour, right? And how fast can you go with a hydrofoil? 0 to 5 knots. So, probably you would not benefit very much from these wings, I would say. And then, of course, one can wonder about the stability of this in roll. Of course, you can have dynamic control, but as we talked about before, in order to benefit from a dynamic control system, you have to have a speed forward. So when this stops, I think you'll have a jolly good time riding on the sea. And if it's stable, it doesn't look stable to me, does it? How can this be stable? Can it be? I mean, obviously the center of gravity is up here. What is the stabilizing moment? There is none. Of course, you could have some propellers that kind of balance, sort of a balance act, some thrusters in water that could balance. But sometimes I wonder about how far people are thinking when they come up with a new concept, right? If you publish this in a newspaper, people will think it's great, right? Looks good. So maybe even you could get some people to invest in it. Some financial people who don't understand too much about technology. But remember this American concept with this enormous ship I showed you? What was it? 1,200 meters long with a landing strip for airplanes on top. And the people who promoted that project were taken to court because of misleading turns out to be technically infeasible. And I would think that could easily apply here as well. Okay. So to summarize, and I'm not going through the entire table, but we have monohulls, we have multi-hulls, we have swath, we have air supported, and we have Vig in ground effect. And you can, this is from a ONR study in the United States, I think, and potential speed relatively to size, sea keeping for size, load capacity for size. And I looked at this table and I don't agree with all of what's listed there, actually. I don't understand why a catamaran necessarily has a poor seakeeping performance compared to a trimaran. Not necessarily so. Depends on how you do it. Okay, but this is kind of a summary of things we have talked about. So you can look at the table and see if you agree. And then you can discuss. Oops, sorry. Okay. Now we'll go a little bit into propulsion, and I'm not going to say very much about propulsion. It's not something I know a lot about. So this is a study for a fuel efficient ship for IW, that means internal waterway. Okay? So one can improve the hull resistance, we have talked about that. One can improve the propulsion and transmission efficiency and the power plant and the utilization. These are certainly factors. You should know something about how can we make a ship more fuel efficient, right? Where are the improvements that we could make? So we're getting a little bit into this thing with propulsion now. We have talked a little bit about engines before, but not very much. For instance, I mentioned, diesel as opposed to heavy bunker being much more environmentally friendly and less emissions. And now we see a new push towards using natural gas as a main fuel to reduce the emissions even further. So LNG on board ships is something for the future. But anyway, just a kind of a starting point. So propulsion systems, and there are many types. Do you know what variable pitch is? The pitching is, the angle of the blades, how much it kind of carves into the water in terms of the angle when it's and you can vary that depending on the speed you are traveling. Supercavitating, I must admit I don't quite know what that means. Twin arrangements we'll look at, and contra-rotating propellers, tandem system, double system, ducts, that is where you lead the water through a channel, or you have kind of a funnel that the water has to go through, and surface piercing, that's a propeller that's partly above water, and it's used in high-speed racing. tip vortex free. Of course, that is swept propellers is something that is very important for submarines, to make as little noise as possible, right? You don't like to have noise generated by the propeller. So therefore, for submarines, you can see some very, very advanced swept propellers. Yeah. Fins aft, before and after the propeller. Combination of propeller and rudder. Of course, if you have what they call the azimuth pod, we have looked at that a little bit before. Rim-driven thruster. That is, you don't have an axis in the middle, but the propeller blades are attached to sort of a cylindrical duct and rotated by motion at the rim. Shuttle, we'll see what is. Tractor propeller. Water jet. That is where you're actually using the inertia of the water. You send it out at very, very high speed. Doesn't even have to be under. It can be above the surface. And today we are seeing, for instance, catamarans, high-speed catamarans that are using this kind of principle. Interesting to see the spray behind the boat. This is a special type of propeller. For lower speed can be some flapping foils, and we also get into this magnetic hydrodynamic interaction, which is another interesting case of innovation, I think. So this is some of these examples. This is kind of similar to a vertical axis wind turbine, just that it's below the surface, and it can give you a push force when it rotates. This is a pump jet, and by ejecting the water at high speed, you get a jet principle. This, you see this, what I mentioned, the surface piercing propellers. So they, above the water, they are in free air, of course, and they cut into the surface, and thereby pushes the boat ahead. So rather big blades, as you can see here. Yeah, here you see some of these variations with ducts. All right, you don't see a axis in the middle. It's the rim that drives the propellers, and you can have different arrangements around the propeller in order to increase the efficiency. And typically with diesel electric, you have much greater freedom as to what kind of propellers you can use, right? So that we are going to see more and more in the future. And then typically a combination of a propeller that you can, turn the direction of the propeller, and thereby also can be acting like a rudder. So you don't need rudders. Yeah. Some more examples of propellers in a nozzle. And this is rim, I think. Is it rim driven? No, it has an axis. Here you see a double propeller, right? and you can increase the efficiency of a double propeller. But don't think that a propeller will give you 100% of the power in terms of a pushing force. I think some of you may know this better than I do, that the maximum efficiency of a propeller is in the order of 60%, isn't it? So you do lose a lot of power, right? And of course, by improving the propeller a few percent, that is very significant. So, for fuel efficiency, I think we are going to see more and more sophisticated propeller system in the future. And more diesel electric or LNG diesel electric type propulsion systems. And of course, when you have two like this, it may be an advantage to. It's certainly not mounted on the long axis like conventional propellers are mounted on the long driving axle, but it's not the case here, of course. It's a mechanical system that makes these two propellers turn opposite ways. And here you see twin. They are mounted on different sides of this axis. And this, I'm sure, is also diesel electric shuttle in a channel sort of thing. And then finally, there's some principle from electricity going back to the days of Faraday's. Have you heard about Faraday's cage? When it comes to electromagnetic waves, you can stop electromagnetic waves by having a metal cage. Faraday's principle. Well, anyway, the thing is that you can buy magnets, and you have water as a electricity conducting medium. By applying magnets to sort of a channel in a particular way, you can make the water in that channel move just without any mechanical parts, just by having the electromagnetism applied to the water. You can push the water. And Yamato, I think there was a Japanese warship called Yamato, right? A aircraft carrier. And that didn't end very well, I don't think, during the Second World War, and this didn't end very well either. This was really a high prestige project in Japan in the 90s. I think this was built in 91 or 92 or something like that. And the principle was to show that this magnetohydrodynamic principle could be used to moving ships. So no propeller, no mechanical parts, just by electricity and electromagnets, one should be able to move a ship. And I've been reading a little bit about this, and we won't go very much into the principle, but here you see some of the magnets and the seawater flow in this magnet field, and you need many of these ducts in order to generate more power. So this 6 linked ring magnets to kind of make this push for the Yamato ship, and they had estimated it should go 16, 17 knots, and I think they ended up with 11 or 12. So it wasn't very good news. And they spent millions and millions. So somehow, the theory of this wasn't matched too well, I guess, with hydrodynamics. So you can study this. I think you can see it in a museum in Kobe. Have you been there? No? No? You should find out. You could have seen it. But the interesting thing is, and I'm trying to explain to you, to have the right mind when it comes to inventions and innovations. They can be great, but you can never fight physics, and the laws of nature. So, and I saw on television just accidentally 2-3 months ago, some of the people behind this project, they didn't give up, and they were working on a new system to generate energy from seawater, because the thinking is that, when you have electromagnetism moving water could generate electromagnetic current, right? And that is true. The reverse is true. So they have great hopes now for building these ducts, where the water would go through, and then when the tidal water goes through these ducts, it would generate electricity. But we know, when you calculate the energy density in water, and let's say it's moving 1 to 2 meters per second, I mean, it's a hopeless project. It's a hopeless project because the amount of energy you'll get out of it is just ridiculous, and you have to have these very expensive systems of magnets and all that. But people don't give up. So, I guess there will be more wasted money. Okay, I think that's the last one on the ships. Anything that I have not talked about that I should have talked about? Can you think of something? Maybe next year I could add something. Well, if you have an idea, so just let me know. Okay, shall we take a deep breath and then continue? And now we are moving very far north or very far south to the Arctic, and we are going to talk about shipping and offshore activities in the Arctic. So today and most of the time on Wednesday I'll talk about this. And the Arctic, it's really a frontier. Of course, going very deep into the sea is a frontier, but going also to the north and to the south with a lot of unknown factors is a real frontier. That is needing technology. And, it's interesting to go back in history because this Dutch guy from Netherlands, Willem Barents, And you may have heard about the Barents Sea as the big sea, Arctic Sea in the north. He was sure that he would be able to find a passage from Europe to Asia going north. And of course he was right. But he went on 3 different expeditions to prove this, and on the last one he died. So there you see a very dramatic picture with ice around it. So that's how that expedition ended, right? So he wasn't able to show that connection. But certainly, yeah, the idea was right. And probably it was 200-300 years before his time, which often happens. And then, of course, Norway has had some very great polar explorers. Fridtjof Nansen and Roald Amundsen. Nansen was a real scientist. You know, he was first of all a scientist and a great sportsman, but he was an oceanographer, and he was very interested in the Arctic regions. And so he was the first man to cross Greenland on skis. He did that. And he and a guy called Hjalmar Johansen, they were absolutely crazy. They thought they could reach the North Pole by drifting on ice across the North Pole. So they were landed on ice, left by the ship, and the 2 men alone for more than a year on the ice. But they survived, which is quite remarkable. So they were able to get back to Russia, I think. But they didn't quite make it to the North Pole. They were very close to the North Pole. But Nansen built this ship called Fram, Forward. Was a great ship designer called Colin Archer, and some of you, if you are interested in sailboats, the Colin Archer is probably the most sturdy sailboat that you can get. It was developed for the Coastal Rescue Service in Norway. But he designed this ship Fram for ice conditions. So that was the strongest wooden ship ever built. And you can see it at the museum in Oslo. Amundsen used the same ship when he went to the South Pole, and he beat Scott, remember, to get to the South Pole. He secretly traveled in Fram going south, not telling anyone, and he was able to reach the South Pole. But he also did a journey earlier on with a small ship called Gjøa, and he actually sailed this Northwest Passage to the Pacific, going north of Canada and Alaska. So these guys were kind of crazy. So here you can see where Amundsen traveled north of Canada, and this is Baffin Island, I think. Maybe that's Baffin Island. And of course now there's some interest in this area, and there is some controversy between the US and Canada when it comes to controlling this route, because it's strategically important. And of course what is happening now is, I'm not sure if this picture is completely correct, but it certainly demonstrates, there is open sea for parts of the year, north of Siberia. So the northeast passage, this one is called northeast and this is called northwest. The northeast passage is easier to traverse than the northwest passage. And this year in particular, year 2010, marked a kind of a new era in commercial shipping in the Arctic. There have been more ships going through the Northeast Passage this year than any other year, including a passenger ship for the first time. So what is of interest is the minimum ice distribution. And these maps sometimes look a little bit different. But one important thing is to distinguish between summer ice and winter ice. Because even now, when the climate is warmer, we still have full coverage, more or less, of winter ice. But it's the summer ice that is much more confined, not so large in extent as it was previously. And that means, since the winter ice is small, since the summer ice is small, the amount of ice that survives the summer is smaller than before. And that means that the area that has multi-year ice, right? Ice that's accumulated over many years, that area is getting smaller and smaller. That's the area where the ice pack is thick, right? When it accumulates, it snows and freezes over several years and accumulates, then it can get to many meters thickness, whereas where you have only year ice, that is waters that have been open during the summer but frozen in the winter, then the ice thickness typically only will be 1 meter or 1.5 meters. And that's important to understand. So here you can see the Arctic sea ice extent in millions of square kilometers. So huge areas, of course. And you see, there's not much variation between these years when it comes to the extent of the winter ice. So during winter, it freezes up there. You cannot do shipping during the winter because it freezes. But in the summer, there's a great variation from year to year, and particularly this year, 2008, had very little ice, and I think year 2010 also had very little summer ice. And it's the least in August, September. That's the good season for ship traffic in those regions. But it's a relatively short part of the year, right? It's late summer, fall, and then things get too difficult. So there's some statistics about how much transport there is in Northeast Passage and the Northwest Passage. But it seems, nowadays we have satellites that can see very well the ice conditions and do forecasting, and thereby assist in planning sea voyages in those regions, right? So we are going to see more and more traffic here in late summer, and then I guess depending on how climate develops, that period may get longer and longer. Some people have been speculating that the North Pole will be ice-free, but as we saw on that map or that graph earlier, the extent of the winter ice seems to be quite stable. It's the summer ice that is different. So it's not likely that we'll have an Arctic that generally is ice-free. Well, you know, these figures, I've seen 15%, I've seen 25% as the remaining reserves of oil and gas in the Arctic regions. Well, regardless whether it's 15% or 25%, that is pretty important because many of the known oil and gas reservoirs are running out, aren't they? So there is certainly an increasing interest in what's going on in the Arctic to be able to use oil and gas resources that are there, and that it means even if it's on land, you know, it's so far away from any populated areas that the only way of getting it out would be by sea traffic, by oil, by tankers or LNG carriers. So here are some of the estimates in terms of billions of barrels of oil or trillions cubic foot of gas. It's of course impossible to relate to, but it is significant resources that are left up there. And it's mainly on the Russian side. See that? Norway has some percent. But then again, you know, there hasn't been much exploration of oil and gas. It's been politically very controversial in Norway to do drilling, exploratory drilling in this region. And there's been some disputed areas. And normally when you divide, you know, the continental shelf between countries, you follow the principle of the midline. That is, the borderline, a point on the borderline has equal distance to the two closest neighboring countries, right? That's the midline principle. Well, the Russians invented here a sectorial principle and wanted to move the border on the Norwegian side, and this has been a dispute going on since 1970, but this problem was kind of resolved this summer, so we don't have that problem. And then you have Antarctica, and that looks like a cake that has been divided by different countries. You have New Zealand, Australia, France, Australia here as well. Then you have Norway. You can wonder, well, what is Norway doing down in Antarctica, right? Actually, a good piece of cake. And that is due to the history and the explorers, right? Norwegian explorers that have been down there. Argentina and so on. So there's a treaty that is, in principle, the treaty says that this belongs to humanity, to mankind, but there's some administrative privileges for these sectors, as you can see in this map. So I'm not going too much into this. So it has to do with sovereignty, you know, who owns it, and more also defense matters, strategic importance, not so much possibly in Antarctica, but in the Arctic regions. You can understand, you know, as a short way from the Atlantic to the Pacific. The strategic importance of that area is tremendous. So ice-class warships, heavy icebreakers, military exercises, build new harbors, patrolling water. This has become a controversial thing. Under ice operations, what can you do under the ice with submarines? And then there's a great push also for scientific and research missions. And of course, sometimes they are combined with some, let's say, national strategies in order to have the right information and maybe also some control. And the Russians have been very active. You see here in 1977, Russian nuclear icebreaker forces its way to the North Pole, plants the Russian flag. I'm putting a marker. Unfortunately, that ice is moving, so it's, I guess. But in 2007, what did they do? They had a submarine. It's unmanned submarine. Or is that manned or unmanned? I'm not sure. 4,200 meters, I guess it has to be unmanned. Huh? But anyway, remotely operated, planting a Russian flag at the North Pole, underwater. So you see, there is, top-level political attention to the Arctic regions, becoming more and more important. And, there are some think tanks. You know what the think tank is? Where you have people who sit down and think about strategy and so on. And this is one by an institute called Econ. And they have one scenario where the development of the Arctic is dominated by Russia and the oil activities, one that is dominated by ship traffic, and one that is dominated by war games. Well, let's hope that's not the future. So, and I think I'll end pretty soon now. There are lots of challenges, and we are going to talk about ships and structures in the Arctic, and where we have sea ice. We'll talk about what sea ice can be like. Icebergs. Where do the icebergs come from? Glacier, exactly. They don't suddenly come to being in the ocean, but they have been accumulated big pieces of ice, of course, as parts of glaciers, for instance, on Greenland or parts of Canada. And these ice blocks are then either calved or they are pushed into the ocean, and therefore you can meet icebergs. Extreme cold, minus 60 maybe. Icing, big problem for ships and also offshore structures. Humid air that freezes on the structure accumulates. We'll look at that. Of course, dark. At the North Pole, in principle, at the North Pole, you have 6 months of day and you have 6 months of night. That's at the North Pole. It's very far away, and you have a vulnerable ecosystem. And also, it should say here, very bad storms. You know, the Arctic storms can be really, really violent. So, combination of big waves, wind, ice, very dangerous. Okay?